Hi, AP Chem friends. I wanted to do a nice explain video for you guys since I'm not going to be here on Thursday for you to ask me questions in class. So hopefully this will help you move through this worksheet should you need the assistance. Question number 1 asks, how does the percent transmittance of a solution vary with increasing concentration or increasing path length? Well, what we know about transmittance is that it's the opposite of absorption. And we already know that when you increase the concentration, absorption also goes up. So then it should become fairly obvious that transmittance is going to be the opposite of that. Path length, on the other hand, if you can envision more space between your light source and your sample, that light has to travel all the way through the air first before it hits the sample. So if you make that space bigger, there's more molecules, there's more things for that light to go through before it hits the sample. So that is actually going to increase our absorption, and it is going to decrease the transmittance because, again, that light has to travel through more things. All right, moving on to number 2, which asks the absorbance of an iron thiocyanate solution containing 0.0050 milligrams of iron per milliliter was reported as 0.4900 at 540 nanometers. So what it wants you to do is calculate the molar absorptivity, including units, of iron thiocyanate on the assumption that a 1 centimeter cuvette was used. Okay, so that's a lot of information for that problem. So overall, what we want is to calculate the molar absorptivity. So automatically, as soon as you see that term molar absorptivity, you should be thinking Beer's law, because Beer's law, A equals that funky E L C. This is the molar absorptivity right there. Okay. And then the second thing you should be concerning yourself with is, what the heck is iron thiocyanate? So my recommendation is, if you don't know what thiocyanate is, consult your polyatomic ion chart. And then if you cannot find it on there, you should look up what thiocyanate is so that you can make that ionic compound. Okay. So once you know what iron thiocyanate is, you can use this information right here to actually do a calculation and figure out what the molar mass is of iron thiocyanate as a whole, so that you can do a little bit of conversion. Okay. So as I was saying, our first piece of information tells us that we have 0.00500 milligrams of iron per milliliter. So we first want to convert that to grams, but that's pretty easy. All you have to do is tack on a times 10 to the negative third onto that. Okay, and that's going to change our milligrams straight over to grams, because we want to convert grams to moles so that we can get a concentration, which is what we're going to use in Beer's law. The second thing to realize is that this is saying grams of iron per milliliter, but the question is asking about iron thiocyanate as a whole. So once you figure out that iron thiocyanate is FeSCN3, which I'm sure that you can Google and figure out very quickly, then you have to figure out, okay, well, I need to convert to moles of iron so I can figure out how many moles of iron thiocyanate I have. And thankfully, for every 1 mole of iron, there's 1 mole of iron thiocyanate, because there's only 1 iron in that compound. So all we realistically need to do here is take this gram amount and convert it to moles of iron. So when I do that, I get that my amount of moles of iron is 8.953 times 10 to the negative 8th moles of iron. Okay, so if you are not sure how to convert between moles of iron and grams of iron, vice versa, I suggest you look at your mole map. All right, so once you have this information, you know that this is the same thing as saying moles of iron thiocyanate. Because again, there's only one iron for every iron thiocyanate molecule. From here, we're going to take that information and we're going to convert it into molarity. We know that molarity is equal to how many moles of solute do you have for every liter of solution you have. So paying attention again to this unit up here, we're seeing that grams per milliliter is what this information is given to us in. So automatically we know that we're dealing with 0.001 liters of solution containing that amount of moles, right? So a simple division will tell you that your molarity of your iron thiocyanate solution is 8.953 times 10 to the negative fifth. Now this number you can finally plug into Beer's law, which I'm going to switch colors to do. So we have an absorbance value that's given to us, 0.4900 is set equal to the thing that we are solving for times our path length, which you should assume, unless you are told differently, that it is 1 centimeter. And then multiplied by our concentration, which we just figured out over here, the 8.953 times 10 to the negative fifth molarity. Okay, so once you solve that out, you can easily solve for E. And if you're not sure what units belong on that, feel free to look it up. It is in fact in the notes. Now, for letter B, it asks what will be the absorbance if the solution is diluted to twice its original volume. So if you dilute something to twice its original volume, you're basically halving the concentration. So quite literally, this number right here, this 8.953 divided by 2 is going to be your new concentration. Okay, so once you do that, you can just plug that new concentration straight back into Beer's law and solve the problem. This one here is asking, okay, well, what if that original solution, so not the diluted concentration, but the original solution, what if we place that in a cuvette and the new path length was 5 centimeters? So you're going to have to sub in a new path length, but keeping our concentration here and keeping the E that you calculated with it, and you're just solving for absorbance. Okay. So that one was a little bit hard. You had to do a lot of converting and assuming based on units. So let's move on to the next part. This asks you to refer to problem 2 again. So we're still dealing with that iron thiocyanate. It wants to know what percentage of light is transmitted by the original iron thiocyanate solution. So recalling that up here, we have an absorbance of 0.4900. So I'm going to write that down here. A equals 0.4900. We know from our notes that the relationship between absorbance and transmittance is A equals negative log base 10 of T. So I want to solve for transmittance. So the first thing I'm going to do is I'm going to rearrange that equation, divide both sides by -1, and I get negative A equals log base 10 of T. Because of the rules of logarithm manipulation, you can solve log base 10 by just raising both sides times 10 to the. So we can say 10 to the negative A is equal to T. So what am I going to do with that information? Well, I'm going to take my A, I'm going to plug in 10 to the negative 0.4900, and that is going to be equal to my transmittance value. And I will have to convert that value into a percent by scooching over a decimal point 2 places. Now, letter B asks you, what concentration of iron thiocyanate will absorb 50% of the entering light? So if it is absorbing 50% of the entering light, is transmitting 50% of the entering light. So A equals 50% and T equals 50%. Okay. So if I know that A is 50% and T is 50%, that makes my solution pretty easy, right? Because I want a decimal for that. So all I'm going to do is I'm going to take that same information that 10 to the negative A is equal to T. In this case, T is 0.5 and A is what we are solving for initially, right? So 10 to the negative A is what we're solving for. We can solve that out and we're going to get A is equal to 0.301. Once I have that A value, I can then again use Beer's law. A equals that funky E times path length times concentration. Now, I want to solve for concentration. I already calculated an E up there, right? I already calculated what that E is, so I don't need to recalculate it again. And I can assume, unless I am told differently, that my path length is going to be 1. So I can easily plug in all those values and solve. Moving on one more time. We have the concentration of yeast tRNA in an aqueous solution is 10 molar. The absorbance is found to be 0.209 when this solution is placed in a 1 centimeter cuvette, and 258 nanometers of radiation is passed through it. So first and foremost, calculate the molar absorptivity. So again, we're going to solve for E. We are given an absorbance value. We are told that the path length is going to be 1 centimeter because we have a 1 centimeter cuvette. And we have a wavelength, which we actually do not need in this situation. And we are also told a concentration. So again, we know what A is. We want to know what E is. We know what our path length is, and we are told our concentration. So this should be a fairly easy problem for you to solve. Moving on to 2, what will the absorbance be if the solution is diluted to 5 molar? Once you figure out your E in this problem, you can use it down here in this problem, plug in a new concentration and recalculate for A. And then finally, what will be the absorbance if the path length of the original solution is increased to 5 centimeters? So again, we're going to use that original concentration. We're going to sub in a path length of 5 centimeters and resolve that problem using Beer's law. Moving on one more time, we have a very lovely practice graph for you. So the first thing that you should do is you should graph all of these points and label your axes appropriately. So your x-axis should always, always, always be your concentration. And if you look at the x-axis very closely, it's labeled such that these values would fit on it very easily. Your y-axis should always be your absorbance. And obviously you are going to label this a little bit more specifically than I have. You will plot your x, y coordinates accordingly, and you should see a line that looks something like this. Then you are asked down below that about the molarities of each of the nickel 2 sulfate solutions at each absorbance. So to calculate for those molarities, you will notice that the concentration up here is not given in molarity, it's given in grams per milliliter times 10 to the negative 5th. So instead of just taking these and saying, okay, well, obviously those are my molarities, they're absolutely not. You have to convert to molarity, just the same way we did way up in the first problem set on the first page, where you had to convert from grams to moles, right? So we have grams in 1 milliliter. So you can easily convert that gram amount to moles and then divide by 0.001 to get your molarity. If you're not sure how to do that, again, I did it up in that first problem set, and I did include a couple of sample calculations on my key, so you can go ahead and take a look at those. My molarities are listed up here next to the absorbance values. Next, we have problem number 6, which unfortunately got split between 2 pages. A 2.845 gram sample of an unknown compound containing cobalt, a cobalt-2 ion, was dissolved in water in a 250 milliliter volumetric flask. The absorbance of this solution was found to be 0.2195 at 515 nanometers in a 1 centimeter cell. Is it possible to use Beer's law to calculate the concentration of the ion in solution? If so, do it. If not, explain what further information you would need. So, recalling once again that Beer's law is absorbance is equal to that molar absorptivity times path length times concentration. To adequately solve that problem, you would need to have 3 of your 4 possible variables. So what I'm asking you is, do you have enough information or do you not? You can figure that out all by your lonesome and let me know. Problem number 7 moves on to giving you some data, giving you an actual graph of that data, and then down below that, the equation of that graph is listed. So let us recall really quickly that we can compare that to Beer's law. This mx is going to be this bit of information. X, of course, is concentration. That EL is the M part. Okay, and then absorptivity is going to be your Y value. So if it asks you to calculate for something, that's how you would do it, subbing in for the appropriate values. First question it asks you is, with the aid of the chart shown, explain why the incident light might be set at a particular wavelength, in this case 640 nanometers. 640 nanometers falls in the red spectrum, and it also tells you that nickel 2 ions are green in an aqueous solution. So the solution is green, but we're using red. So if you are unsure as to why we're using red to analyze a green solution, I would refer you to the notes that we took in class on Monday. And then same for part 2, discuss why it would not be appropriate to use any wavelength in the 495 to 570 nanometer range. Again, the solution is green. Why is it not appropriate to use a green wavelength to analyze that? Letter B asks you, what is the relationship between absorbance and transmittance of the incident light? You could cite the equation that shows their relationship. You could talk about the opposite nature of them. Either way, whatever makes you happy. Letter D asks you to determine the concentration of the unknown solution of nickel 2 sulfate, given that it exhibits an absorbance of 1. So we're giving you an absorbance value, 1, and I want you to solve for the concentration. So we're calling that relationship that I cited up here, and you're going to use this equation, plugging in appropriately to solve for X, which is concentration. And then our last problem, magnesium chloride solution is colorless and transparent. Comment on the usefulness of a spectrophotometry experiment for the analysis of a solution of magnesium chloride. Explain your answer. Your key words to pay attention to is that that solution is colorless and transparent. Can you use spectrophotometry to analyze a colorless and transparent solution effectively? Not can you do it, but can you do it effectively is my question. So hopefully this video was helpful for you. If you have further questions, feel free to talk to me about it next week in class.